All right, so this week I think we had the second probability section and chapter 4, which is the discrete probability chapter. Do you have any questions about the notes? I'm kind of hoping, and I didn't send out an email this week, but I'm kind of hoping, crossing my fingers, that before you come to this meeting, you at least get to watch Wendy Lightheart's videos, or at least look through the notes to make sure that you know what's coming. So I'm hoping you're all doing that, because then this meeting becomes a lot more valuable if you do that first. Hi, Casey. I'm recording this video for Moodle. I'm gonna put this recording on Moodle after, probably not till tomorrow, because that's how long it takes Zoom to get it done, but I'm just making sure that's okay with you. So can you give me a thumbs up?
Yeah, it's good.
All right, thank you. Thank you. All right, so here we go then. I'm just gonna, yeah, so it's fine if it's just to look at it, and then, because what I think the most useful thing to do in this session is to just, I kind of do my homework assignment, and then if people have trouble with it, they can go back and look at the video later or whatever. So I think that's how we're going to structure these meetings from now on. And then the midterm week, I don't think I'll put the class on, and you can work on the test during the meeting if you want, but I'm not going to record that one. Let's see. So I'm going to share my screen. So hopefully you're all seeing the chapter 3B homework, right? Yes. Good, thank you. All right, so, and you can post to chat, and I may not see it for a minute, so just be patient with me. But we're talking about probabilities again in chapter 3B. So according to Master Foods, the company manufactures M&Ms. 12% of peanut M&Ms are brown, and it goes through this list of M&Ms. So let's see, what do we got? 1, 2, 3, 4, 5, 6 different colors. I didn't even realize there are 6 different colors of M&Ms. So we think about it, you want to know the probability that a random selected peanut M&M is not green. So 15% of them are green, and the rest of them are not green. So if you think about it, that would mean that 85% of the M&Ms are not green, right? So that's going to be 85% or 0.85. Probability that a selected peanut M&M is green or yellow. Well, let's see, we have 15% green, 15% yellow. So that's 30% total are green or yellow. So we put 0.3. Compute the probability that 3 randomly selected peanut M&Ms are all yellow. Okay, so we got some work to do here. So let's see, 3 randomly selected peanut M&Ms are all yellow. So if we assume that we have 100 M&Ms, so I think that's the way we're going to have to do it. We assume that we have 100 M&Ms, then we have 12 brown, 15 yellow, 12 red, 23 blue, 23 orange, 15 green. So compute the probability that 3 randomly selected M&Ms are all yellow. So if you pick the first M&M out, the probability it's yellow is 15 out of 100. Okay, and then now they don't really say with or without replacement, but let's just, well, picking 3 means it's going to be without replacement. So if you pull 1 yellow M&M out, there's 14 yellow M&Ms left out of 99 M&Ms. And then the third time you choose, there'll be 13 yellow ones out of 98. So you'd actually have to make that calculation. Let's see if that's what they're trying to get after. So we'll go to the calculator and we'll do that. So 15 divided by 100 times 14 divided by 99 times 13 divided by 98. I get 0.0028. If all goes according to plan, that's going to be my answer. Wrong. 0.0028. So I wonder if they just do 0.15 to the third. Let's see if that's what they do. 0.15, because 15% times 15% times 15%. So let's see if that's what they do. 0.0034. So that assumes you'd be putting the yellow M&Ms back. Yeah, so they didn't really explain that too well. But they're saying we're going to take a yellow M&M out, we're going to put it back so it's still 15% on the second try and 15% on the third try. So that was not a well-phrased question, in my opinion. If you select 6 peanut M&Ms, compute the probability that none of them are orange. So I got 23% are orange. So that means that, what, 77% are not orange. So we just do 0.77 times 0.77 times 0.77 6 times. So 0.77 to the 6th power. So that should be my winner there, 0.2084. And then if you randomly select 6 peanut M&Ms, compute the probability that at least one of them is orange. So this one's interesting because you're like, oh my word, there's a bunch of different ways that at least one could be orange. So the way we're going to think about it, probability at least one is orange. So that's like if 1 is orange, 2 is orange, 3 are orange, 4 are orange, all the way up to 6 are orange. That's going to be 1 minus the probability that 0 are orange. And that's that complement thing working. So that's going to be the best way to do this problem. So probability that none of them are orange would be 1 minus that answer from the last one, 0.1 minus 0.2084. So what's that going to be? 0.7916, I think. Let's see. Yeah, so that works. So that's that complement thing. That's a really powerful thing to be able to use. So that's number one, y'all. What do you think? What questions from that one do we have? Anything? I don't see anyone putting anything in the chat. So
For A and B, how would we like calculate it? Would we have to like add all the percentages up and then minus like the not green or yellow or stuff like that?
for A and B,
Yeah.
so compute the probability that a randomly selected peanut M&M is not green. So 15% are green, right? So that would mean 85% are not green. So then we would just put 0.85.
Okay.
And then compute the probability that randomly selected peanut M&M is green or yellow. Well, 15% are yellow and 15% are green. So that makes 30% therefore are yellow or green. So that's where the 0.3 comes from.
Okay, thank you.
So we'll probably end up skipping a couple like we did last week if there's repeats. So let's see what number 2. Okay, number 2, you toss a fair coin 4 times. What's the probability that you get all heads? Well, fair coin means there's 50% chance that you get a head, then 50% chance on the second one, 50% chance on the third, 50% chance on the fourth. So it's like you're multiplying 0.5 by itself 4 times. So let's see what that says on the calculator. 0.5 times 0.5 times 0.5 times 0.5, or just 0.5 to the 4th. So 0.0625, would be the probability of getting all heads. And then at least one tail, well, at least one tail, if you think about it, that's the complement of getting all heads, isn't it? At least one tail is going to be 1 minus the probability that you get all heads. So 1 minus 0.0625 is that 0.9375, I think. All righty. There's a good chance some of you have these same versions too, so that'd be pretty neat. Okay, questions on number 2? All right, number 3. Suppose that 17% of people own dogs. If you pick 2 people at random, what's the probability that they both own a dog? So in that case, it's 0.17 for the first person times 0.17 for the second person. And let's see if we do that in our calculator. Basically, it's 0.17 squared, so 0.0289. So you pick 2 people at random, 2.89% of the time, both of them will be dog owners, according to this scenario. What do you think? So far, so good, everybody? All right. Number 4, let's see. Yeah, every cereal box has a gift inside. Those were fun back in the day. But you cannot tell from the outside what the gift is. The store manager assures you that 14 of the 42 boxes on the shelf have the secret decoder ring. So we're in that movie, A Christmas Story. Okay. Thanks for letting me know, Grace. Okay, so let's see. Cereal boxes, so 14 out of 42 have a secret decoder ring. The other 28 boxes on the shelf have a different gift inside. If you randomly select 2 boxes of cereal from the shelf to purchase, what's the probability that both of them have the secret decoder ring? Well, 14 out of 42 times 14 out of 42, right? They're independent events. What's in one box is independent of what's in another one. So we got 14 42s for the first. My pen's not cooperating. That should be a 42. So 14 42s times 14 42s. We go to our calculator. And let's see what we get. We get 0.1 repeating, 0.1111. So, I got it wrong. Okay, let's see what's happening. The store manager assures you that 14 out of, so this one I'm not. So, because we're talking about the shelf in a store. So once you choose a box, there are what left? There are 41 left. And once you chose a box with a decoder ring, only 13 of those remaining boxes will have the ring, right? So 14 out of the first 42 boxes have the ring. Now you chose a box that has the ring in it. So you got to set that aside. And now out of the 41 boxes that are left, 13 of them have the ring. So we actually have to make that calculation. So I did not read the question carefully enough. So 14 42s times 13 41s. It's going to be slightly different, 0.1057 instead of 0.1111. So 0.1057. Okay. So that one, that you didn't replace that box. That's the reason why that box was not replaced. So number 5 kind of speaks to this same situation. number 5, you have 2 different scenarios. The first scenario, we have what, 21 marbles in this bag, and you draw one at random, then you put it back in, then you draw another one. So there's 21 marbles in the bag on both picks. So the first one, to choose a white one on the first one, would be 6 21sts. And then you put the white one back, so you still have the 21 marbles in. Now what's the probability you choose a green one? 7 21sts. So then we make that calculation. 6 21sts times 7 21sts. And we get 0.0952. Okay, so watch what changes then in the second case. We have 8 black. Oh, well, we still have 21 marbles, but we have different colors now. Black instead of what? White. Still got green and blue. Okay, if 2 different marbles are drawn from the bag, what's the probability of drawing first a black marble and then a blue marble? So this one doesn't tell us we're putting the marble back in the bag. So 8 21st is going to be the probability of drawing a black one. Now there are 20 marbles left, and then we want to draw a blue one. There's still 6 blue marbles in there because the first one we chose was black. So now we have to do that calculation. So let's see, 8 21st times 6 20ths. So I get 0.1143. Okay, so that's that whole difference between replacing the marble and not replacing the marble. Monse?
I had tried the last question, the cereal box one. I had different numbers, but I still tried to do the same exact thing, but mine came out wrong.
What were your numbers?
Mine was the store manager assures you that you have 17 of the 54, and then the other 37 are on the shelf. So I had done here 15 divided by 16, or hold on, sorry. Oh yeah, 17 divided by 54 times 16 divided by 53. Would that be right?
That's what it should be.
Okay. Yeah, and I got sorry, 0.09503.
Okay, let's see. Yeah, my computer's not liking having so many programs open at the
It's
same
okay.
time. So let's see, 17 over 54 times 16 over 53.0950.
Oh, I see. Okay, I read it wrong. Sorry.
Okay, no problem. So we got it now.
Let me double check. Okay, yeah, it was right. That's my bad.
Okay, no worries. Good. We figured it out. All right, so now we got a bunch of these ones where they give you tables. All righty, so we can go over a couple of these, but then you all can figure it out from there. But you, in question 6, you got given a test to a group of students. The grades and gender are summarized below. So 16 male students and 5 female students got A's, 14 and 17 got B's, 6 and 11 got C's. If one student is chosen at random, find the probability that the student was male and got a B. So students that are male and got a B are 14. Okay, so there's 14 students to choose from out of 69 total students. So we would just do 14 divided by 69 in our calculator. 14 divided by 69. So I get 0.2029. And that's the way all these table problems work. You just look at how many fit the description over the total. So like for the next one, find the probability that the student was male or got a C. So male or got a C is going to be these students right here. Right? Don't circle the totals. The body of the table, the 11, 14, 5, 6, 8, and 4, that's where you want to circle the values from. So male or got a C is going to be that, what, 25, 30, 34 students out of 48. So that would be what we'd calculate is 34 out of 48. And we get 0.7083. Alrighty. So that's how these table ones work. Those aren't as difficult as the last ones we did. But let's see if there's some conditional probabilities down here that we might get into. Or what questions on those two do we have? What questions on those two? Any? Okay. Okay, so this next one, I think that you can answer the first three pretty good, but let's talk about part D, because this is a conditional probability. If one student is drawn at random, find the probability that the student was male, given that they got a C. So we know that this student got a C. So therefore, the only students we are interested in are these ones right here. We're interested in figuring out what's the probability the student was male, given that they're in that column. So all you would do, there are 20 male students out of 32 that got C's. So you would just do 20 divided by 32. Oh, I got to go to my pen. Here we go. So 20 divided by 32. So you'd make that calculation. Let's see, can I do that in my head? I think it's 0.625. Yeah. Alrighty, so with these these conditional probabilities, in the formula is this: probability that A happens given that B has happened, right? So this is probability A happens given that B has happened. So we already know in this case that we wanted to have the C's. So we know that we're choosing from the C column because we already know that person got a C. There's a formula for it. It's the number of ways that A and B happen together over the total number of ways B can happen. Okay, so if you look at that, it's the same thing. Number of ways that you got a male and a C are going to be 20, and the total number of C's was 32. So you do 20 divided by 32. Alrighty, so that's the formula. The other way you might see the formula is probability that A and B happen divided by probability that B happens. So that could be the other way that you see the formula for this. Alrighty. So that's conditional probability. So what questions on that before we scooch to number 9? Okay. Well, let's clear out these drawings and see what we got going next. All right, so let's look at this one. A CBS News poll involving a nationwide random sample of 651 adults. Asked those adults about their party affiliation and their opinion of how the US economy was changing. Getting better, getting worse, or about the same. The results are shown in the table below. Okay, so probability that one randomly selected person in this is a Democrat, we'd have to add up those three values and divide it by 651. So the way that would look on our calculator is we would actually, you got to use your calculator with the parentheses sometimes, so we could make this calculation on our calculator. So that's the number of Democrats over 651. So that's actually going to be the calculation that we make. So let's see, 12 plus 87 plus 137 divided by 651. So we get 0.3625. 0.3625. So that's the probability that you have a Democrat if one randomly selected person. So probability that the randomly selected person thinks the economy is worse, you would add those three numbers and divide by 651. So I'm not sure what that works out to be, but I can, I think you all can handle that one. And then probability that the economy is worse, given that you chose a Democrat. Okay, let's talk about that one. So we'll talk about this one right here. This is going to be the number of people who thought it was the economy's worse and are a Democrat divided by the number of Democrats, according to that formula that I just wrote up above. So worse and Democrat is 137. Total number of Democrats is going to be those added up again. So let's see, can I do that in my head? Is that 236 if I add those in my head? 87 and 12 is 99. 100 plus 137 is 237, but it's one less than 100. So 236. I mean, that's what I'm sticking with. All right, let's see. 137 divided by 236. Let's see if we get it right. So 0.5805. All righty. So you think to yourself, this is probably the same thing. Democrat, given that it's worse, is probably going to be the same thing, right? That's what you think, but you got to be careful. Watch what happens here. So probability Democrat, given that it's worse, that's going to be number of Democrats and worse. So that's still 137. But the bottom this time, the denominator is going to be the number of worse people. So let's see, I may have trouble calculating that. You would add these three numbers up. So let's see what we get. 19 carry the 1, 5, 8, 9, 299 if I'm not mistaken. So 137 divided by 299 on my calculator. See, I'm just going to use my handheld one. I think that you probably don't need me to demo how to do a division on my calculator, so I'll put it on, do the one in my hand. 4582 is what I come up with. Last but not least, probability Democrat and worse. You would actually have to do Democrat and worse are going to be those 44. Oh, wrong. I circled the wrong number. Democrat and worse is 137. And then the total number of people was 651. So I'd just do 137 divided by 651. So 0.2104 is what I'm coming up with. All right, so there's number 9. That one was a little bit more involved because of the 2 different conditional probabilities. So what do y'all have on that one? Nothing? All right. Moving on.
Sorry, I couldn't hit my, I was doing it on mine.
Okay.
Sorry, on the last problem. And my D, I didn't get right.
Your D you didn't get right. You want to should we see it real quick? Can you
Yeah.
share it, Casey? I'm going to stop sharing mine and then you can share yours.
Okay.
And
It's,
see what's going on.
just hit the share button, right?
Yeah, hit the share button and just choose the correct window. There we
There.
go.
Okay. So this one here.
Okay, let's see. So Democrat, given that is better, Democrat and better is 12. So you should have done 12 over 71.
Okay.
So let's see if you do 12 divided by 71. That's probably going to be the ticket.
Yeah, I added all these on divided by these, but that was wrong.
Yeah, Democrat and betters, 12 of them, and then yeah, total number of betters 71. So just do 12 divided by 71.
Okay. That makes sense then. Thank you.
Okay. Okay, so let me go back to Sharon here. Let's see. So that was a fun little problem. How many are in here? Holy smokes, I didn't realize there were that many questions on this assignment. But we better step on it because the next one's got some pretty intensive calculator work. So let's do 10 though. 10's a good one. Find the probability, use the probabilities to answer the following question, round to 4 decimal places. So, right, we're just going to use the formula. Probability of B given A would be the probability of B and A. B and A is the same as A and B. So these two are going to be the same. Divided by probability of A. So I'm going to do 0.10 divided by 0.24. And let's see what we get. 0.10 divided by 0.24. I get 0.4167. Okay. So it's just straight up just use the formula for that one. So that one should be pretty straightforward. The next one could be interesting because it looks like they give us probabilities instead of the numbers. So let's see. Oh, okay, plus you doing this mutually exclusive business. So Pew Research asked 1,306 Americans, from what you've read and heard, is there solid evidence that the average temperature on Earth has been getting warmer over the past few decades or not? The table below shows distribution of responses by party and ideology where the counts have been replaced by relative frequencies. Relative frequencies are basically the percentages. So are believing that the Earth is warming and being a liberal Democrat mutually exclusive. It's mutually exclusive if this number right here is 0. Right, so that would mean that they don't happen at the same time, but you do have liberal Democrats believing that the Earth is warming. So this one I'm going to say not mutually exclusive. So let's see if I got it right. Not mutually exclusive on that one. Okay. So what is the probability that a randomly chosen respondent believes the earth is warming or is a liberal Democrat? So for that one, we're gonna actually have to add these numbers up plus these numbers. Okay, because that's gonna be the either or. So let's see what we get. I think I got 0.62 when I did it in my head. Yeah. So it's because those four different percentages are the people that believe the earth is warming. These three different percentages are your liberal Democrats. You're not going to add 0.8, 0.18 twice. You're just going to put it in there once. Add up those 6 relative frequencies and you got your answer. What's the probability that a randomly chosen respondent believes the earth is warming, given that he is a liberal Democrat? So you look at this row right here, you got 0.2 are liberal Democrats, 0.18 are liberal Democrats and earth is warming people. So we're going to do 0.18 divided by 0.2 for this one. So that should be 0.9. So then you just go through with that, the rest of them. Let's see about this independent one. Does it appear that whether or not a respondent believes the earth is warming is independent of their party ideology? I'm going to go that they're dependent. Because, you know, it definitely depends on what side of the aisle you come from, whether you believe the earth is warming or not. So there you have it. Those are dependent. Mathematically speaking, we can prove it as well, right? To be independent, this has to be the case, right? To be independent, the probability of A given B has to be the probability of A. So conservative Republic. So if you think about probability that the earth is warming, given that they're conservative, equals probability that it's warming, then they'd be independent, right? Well, the earth is warming people make up 60%. So the right hand side of this is going to be 0.6. Probability you are believe in warming, given that you're a conservative Republican, is only going to be 0.11 over 0.33. So it's going to be 0.33. So those are not equal. Since they're not equal, then they have to be dependent. All right, those would have to be equal in order to be independent. That dependent and independent is one of the trickier ideas, in my opinion. What do you think? Any questions about that? That's why I picked that they're dependent and not independent.
For D, since it says the earth is warming, given that he is conservative, would we do the similar thing that we did on C?
Yeah, so the conservative Republican people are in this row right here, right?
Yeah.
So you do earth is warming and conservative Republicans 0.11 divided by probability of a conservative Republican is 0.33. So if you do 0.11 divided by 0.33, you get 0.3333 in my case. Does that make sense, Monse?
Yeah.
Cool. All right. Let's see. So I think that you can kind of do the same. You can figure out F given that info then. But let's see what else we got going down the rows here. So we got tables again. So you can figure out the tables. How many tail? Good, we got a lot of tables. So 16 might be interesting. So a jar contains 8 red marbles numbered 1 to 8 and 10 blue marbles labeled numbered 1 through 10. A marble is drawn at random. Find the probability of the given event. Oh, we need to do reduced fractions finally. Okay, so there's 18 total marbles. Find the probability that the marble is red. Well, there's 8 red marbles out of those 18. Reduce that fraction. We got 4/9. Okay, find the probability that it's odd numbered. Well, you got 4 odd numbers between 1 and 8. You got 5 odd numbers between 1 and 10. So there's 9 out of 18 odd numbers. That's one out of 2. Then you get the tricky ones. So red or odd. So you got 8 red marbles. And then or odd. Well, 4 of the red marbles are odd. We're not going to count those again. Those have already been counted with the 8 red ones. But then there's 5 blue marbles that are odd. 1, 3, 5, 7, and 9 out of your total 18. So we do 13/18. That's a fraction that can't be reduced. So 13/18. Then we do the same exact thing for blue or even. 10 blues plus 4 reds. 10 blue or even. And then 4 more even from the red. So you got 14 out of 18, which is 7 out of 9. Alrighty, so that's kind of the way you run through those ones. What do you think? Questions on those? Okay, so let's see what we got going on this one. Survey of athletes in a high school is conducted. The following facts are discovered. 15% of athletes are football, 41% are basketball, and 22% are both. Athlete is chosen at random from the high school. What's the probability that the athlete is either a football player or a basketball player? So there's a formula. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Because the A and B might be in the A or the B, we have to subtract it out so we don't double count it. So for this one, you got 57% football, 41% basketball, and then 22% play both. So we have to make that calculation right there. I guess 0.76. And they want it as a percentage. So instead of 0.76, I'm going to put 76. Because they wanted it as a percentage, not a decimal. Okay. That one's not bad. So this one I'm going to let you struggle with because we really ought to get moving on because the next section's got a lot of technology in it. So this one, just read the table, count up the total number of people, divide that total number by whatever fits the category, and those are your probabilities. All right, so we've done marble ones already, cookie one just like marble one. So this one's like the M&M problem up above, right? a special deck of 10 green, 13 blue, and 6 red. So there's 29 in the sample space, right? Because there's 12. Oops, I got it wrong. Did I not count those right? 10 green, 10 green, 13 blue, and 6 red. When a card is picked, the color is recorded. The experiment consists first of picking a card and then tossing a coin. So there's actually going to be 58 in the sample space, because you could do a green, pick one of the 10 green cards and a head, or one of the 10 green cards and a tail. So there'd actually be 20 different things that could happen with the greens, 26 with the blues, and then 12 with the reds. Okay, let A be the event that a green card is picked first, followed by landing a head on the coin toss. So find the probability that that happens. So to pick a green card first, you're going to have 10 out of the number of cards. So 10, the total number of cards there is going to be, my pen's got a mind of its own again. 10 out of what, 23, 29? That should be a 0. Then times 1/2. So I should make that calculation there, and let's hope it works. Let's see, 10 over 29 times 1 over 2, 0.1724. Okay, so let B be the event that a red or blue is picked, followed by landing a head on the coin toss. Are the events A and B mutually exclusive? So can you pick a red or a blue followed by a head at the same time that you can pick a green followed by a head? I think they are mutually exclusive, because you can't pick a red or blue at the same time you're picking a green, right? So the event for red or blue followed by a head is like RH or BH, and then the event of a green followed by a head is like GH. They cannot happen at the same time. But I bet you A and C are not going to be mutually exclusive. Let's see. Let C be the event that a green or blue is picked, followed by landing a head on a coin toss. Are the events A and C mutually exclusive? Well, A is green then head. C is green or blue then head. So definitely A and C can happen at the same time. If you pick a green, then roll a head, they can definitely happen at the same time. So no, they're not mutually exclusive, because they can happen at the same time. All righty. Okay, let's see the dice ones. This one, 24 is interesting. A and B are independent events. And then probability of A is 0.58. Probability of A and B is 0.04. So if they're independent, then probability of A and B equals probability of A times probability of B. So probability of A and B equals probability of A times probability of B. So this is going to be 0.04. Probability of A is 0.58. And then you got probability of B here. So we would just do 0.04 divided by 0.58. And we get 0.0690 if we go nearest 4. 0.0690. Okay. 25, if J and K are independent, you got probability of J given K is 0.54. If they're independent, probability of J also has to be 0.54. That's just how independent events are defined. So we know that K has happened, so the probability J happens is 0.54. If J and K are independent, it doesn't matter that K happened. It's going to have the same probability. That's why it's 0.54 again. And let's see. All right, I think the rest of them you can get through pretty okay. We got that. We just used half the class on that section. I didn't realize that it had 28 questions. I thought the other section was bigger. So, but what last minute questions do you have on that section? We good? So we'll move on to the next section then. So let's see. So the next section was this one here, chapter 4, homework. All right. So probability distribution tables. Basically, it's a probability distribution table if the numbers in the P of X column, this P of X stands for probability. So it's saying that the probability that 53 happens is 0.4. So these two numbers should be different. Hopefully in your table it's different. It's not going to matter because what you're going to do is you just consider that all the probabilities got to add up to 1.0. That's the same with any probability distribution. The probabilities are all going to add up to 1. So far I got 0.8 in there. So to get to 1, I'm going to have a 0.2. Simple as that. And yeah, this section make a lot more sense if you read the book and or watch the video first. Okay. So the next one, suppose that you are offered the following deal. These are kind of cool problems. You roll a 6-sided die. If you roll a 6, you win $19. If you roll a 4 or a 5, you win $4. Otherwise, you pay $8. Okay, so what we're going to do, the X is going to be like the expected amount you win or lose. So do they want us to do 4 decimal places? Okay, so if we roll a 6, we win $19. So $19 is going to be the value there. 1/6 is going to be the probability because we got a fair 6-sided die. 1/6 is going to be the probability. If we do that to the nearest 4 decimals, it is 0.1667. Now, I ran into this mistake before. I believe I didn't read the directions. It says list the X values where X is the profit from smallest to largest. So obviously the largest X value then is going to be 19 with a probability of 0.1667. I'm going to lose $8, so -8. And I'm going to lose that amount if I roll a 1, 2, or 3. So that happens 50% of the time. And then I'm going to win $4 if I roll a 4 or a 5. That's 2 out of 6. So 0.3333. And there we go. We got it right. Okay. This is why I wanted to spend more time on this section. Find the expected profit. Now, if you have your computers open, and this might go too fast for those of you that are here with me now. So if you go back and watch this again, then you can pause the video. But what I'm gonna do is I'm gonna open what's called a Google Sheet. And Google Sheets are gonna make these calculations much easier. So I'm gonna open up a new window because I want to see both windows side by side. And then I want to go over here. And if you go to Google, there's a apps right here. You go to Google Apps and you hit Sheets. Now, if you don't, the three of you that are with me now, if you don't have access to those, then this Google Sheets, we can figure out how to get you access. That goes for anyone that's listening too, but I'm gonna go to Google Sheets. And I want to open a new blank spreadsheet. Now, spreadsheets are incredibly useful in a lot of different situations that come up in math and in life in general. You can use a spreadsheet to do budgeting. You can use spreadsheet to, I don't know, keep track of, I don't know, what you lift, what weights you lift. I don't know, it could be anything. So what I'm going to do is I'm going to enter my table in. So I'm going to enter -8, 4, and 13. And I'm going to enter the probabilities 0.5, 0.3333, and 0.1667. And then the formula for this expected value, the formula is this. Expected value or mean, they use the Greek letter mu for mean or expected value. And it equals, this means sum, it's the Greek letter sigma, sum of x times p over x, p of x. So we gotta multiply the first column by the second column, and then we gotta sum up this new column. So it's really easy to do on Google Sheets. So what I want to do is I want to multiply the number in A1 by the number in B1. So I'm going to go equals A1, and that tells me I'm going to start with that number in that cell multiplied by B1, and it gives me that number right there. Then I can copy that formula. Instead of having to write that formula every single time, I can copy that formula into the other spaces by just clicking and dragging on that circle on the right. So what that did when I copy the formula is it actually, as you can see, the box is highlighted, it actually did A2 times B2. And then this one's A3 times B3. And that's what we needed to have happen. So that's going to be the X times P of X column. Now I want to add those numbers up. So now I can just choose some other spot like down here somewhere. And I want to add those numbers up. So I'm going to go equals. You always start with an equals when you're putting a formula in. And I want to do sum. And right there, it should pop up sum C1 to C3. That's going to sum up the three numbers in that column. Summing up C1 to C3. That's my expected profit from this game. All right, my expected profit from this game is -0.4997. And that's what I'm going to put round to the nearest cent. So -0.50 cents, right? And they don't like that. What do they like? Oh, they came up with a positive. Oh, because I got 13. It's supposed to be 19. Ah, that'll make a difference. Yeah, so there you go. That was supposed to be 19 right there. So there, now I got 0.5, 0.50 cents. Okay. So expected profit I'm gonna make is 50 cents for each time I play this game. Interpret the expected value. If you play many games, you will likely win on average very close to 50 cents per game. And then when you will win this much if you play a game. And then this is the most likely amount of money you will win. It's going to be the first one. All right, because it's going to be, that's the amount of money you expect to win each time you play the game on average. Certainly there's going to be a lot of times where you're going to lose the $8. There's going to be a couple times you win the $19, few times you win the $4. But on average, each time you play, you expect to gain 50 cents. Based on the expected value, should you play this game? Well, you're going to make on average 50 cents every time you play it. So I'm going to say yes, but let's figure out which yes we should choose. It's not the third one. We got to choose we're going to do it based on our expected value. The expected value is not 0, it's positive. Yes, since the expected value is positive, you would be very likely to come home with more money if you played many games. That's the one I'm going to choose. The expected value is negative. You say, no, I'm not going to play that game. All right, let me pause and see if y'all have any questions on that one. I know we introduced spreadsheets into this. We haven't even got into the binomial and Poisson distributions where we're going to use our calculator. So it's a lot. I think that's the reason why they didn't do anything. Well, they did one new section. Chapter 3 could have been assigned last week, but everyone would drop the class then probably. So what questions from this one? I think we should do another one of these for sure. So let's look at the next one down. Okay, mean of this probability distribution. Mean and expected value mean the same thing. All right, so we could do questions 3 and 4 the same exact way. All right, so let's do number 4. Just for kicks, because it looks like it's a bigger table. So I'm going to go, and I'd like to have my probabilities in the second column and my numbers in the first. So I'm going to put my scores in the first column here. So 3, 4, 9, 10, 12, 13, 14. Now I'm going to put my probability. So 0.1, 0.1, 0.15, 0.35, 0.01, 0.27, and 0.02. And now you see that kind of my values kind of changed, because now, well, these 3 are going to be correct. That's A1 times B1, A2 times B2, A3 times B3. So I want to basically copy that down to have them all be that same formula. So now, as you can see, it's the same formula. Now I want to add those up, and that's going to be my expected value. So I go equals sum. C1 to C7 is going to be the first option that pops up. That's what I want. So the sum of C1 to C7, 9.46. That's what I would put right there. Expected value and mean the same thing. All right. So what questions on this? All right, I know it's a lot to throw at you. And I don't think Wendy used the spreadsheets in her teaching. She kind of did it all by hand. There's a lot of calculating to do all by hand. All right, let's look at this next one. Is like it works like this one up here where you find your X and your P of X. So I'll let you all do number 5. 6 works the same way that I just did. 7 wants the standard deviation. So that's a whole different formula. Okay, so the standard deviation, so that's the measure of, the standard distance from the mean that a data value is going to be if you chose it. So we use this thing to represent variance. So variance looks like this. It's going to be, I got to make sure I have my formulas. All right, so it's the sum of x minus the mean squared times p of x. That's going to be my variance. And we're going to do it in the spreadsheet, so you're going to see how it looks. Then the standard deviation is just the square root of that number. It's just the square root of that number. Okay, so I want to put that table into my spreadsheet. So we're going to do number 7 together in the spreadsheet. So here we go. So I basically can do 0, 1, 2, 3, then get rid of those. No, my writing's in the way, isn't it? There we go. And then I can do 0.05, 0.15, 0.1, and 0.7. Now let's get rid of those. And we'll get rid of those too. Okay, so now this 2.45 is actually going to be the mean. All right, so that is the mean right there, or your mu, right? That's your mean. Okay, now this column, if I follow this formula up here, right, I'm going to follow this formula right here. So I actually have to do my x value, which are these, minus the mean, and then I got to square it, and then I got to multiply by that column. So it's a pretty involved process here. So what we're going to do is I go up to my, looks like I'm on this cell. So what I got to do is equals, and then I want to do the x, that's going to be this value, A1 minus 2.45. Now here's the deal. If I just put that cell number C9, when I copy the formula down, the next one down is going to use C10. And then if I copy it down again, the next one will use C11. All right. So I want to anchor it. I want it to use 2.45 for every calculation. So what I have to do to anchor that number in is, I put a $C $9, and that is going to anchor it, and it's going to use that cell now for every calculation in this column. It stays on that cell. It's tricky, I know, very tricky. And then end the parentheses. Now I want to square it, so I hit Shift 6. Shift 6 is the to the button, so to the second. So that's the x minus mu squared. And then I want to multiply all that by the B1. I want to multiply that by B1. Enter, and there we go. Suggested autofill. Sometimes it does that. You just hit check, and it copied all those down. And you see how it stayed $C $9. That stays the same for every one of them. And then the A4, B4, A3, B3, those change. Now I want to add those up. So equals sum. Sure, D1 to D7, there's nothing in D5, 6, and 7, so let's just do it. There you go. That is going to be the variance. That's your variance. Okay. Then I want to do the standard deviation. by square rooting that number. So to square root on Google Sheets, we do equals SQRT, begin parentheses, and then boom, hit that value right there, end parentheses, enter. That's my standard deviation. So 0.9206, it appears as my standard deviation. Alrighty. So unfortunately, with these probability distributions like this, these discrete probability distributions, there's not really a calculator app to do. I mean, you could do it inside of the tables on the calculator, but it's so much easier to use the spreadsheets. Let's do one more like this. If we look at number 8, and the beautiful thing is now that these formulas are in there. So I would only have to edit where I have these down arrows, and the rest of them should fill in. So let's see if it works. So X is 1, 5, 10, or 11. And I change my P of X's to 0.08, 0.07, 0.1, and 0.75. And everything now just changed to the new values, right? So those are actually going to be the correct answers. So what was it? 9.68, 9.68, and then the next one was 8.8776. And then the next one was 2.9795. Hopefully we get them all right, and we did. All right. Expected value and mean are the same. So expected value is 9.68 again. All righty. So using technology, that's like the theme here of this whole lesson. All right, what questions before we leave the spreadsheets? Because I think that's the last one where we, yeah. What questions before we leave the spreadsheets and get to the calculator? All right. Once again, use office hours Thursday 10 to 10:30 and 4 to 5, right? If you come across anything or want to go through these spreadsheets together. Okay. Back to my open math. Now we get into the binomial distributions. So binomial distributions basically have a number of trials and they have a probability of success, right? So 54% of all Americans are homeowners. If 37 Americans are randomly selected, find the probability that exactly 19 are homeowners. So this is a binomial distribution. So the way we write it is binomial distribution. X is a binomial distribution, and N is the number of trials, P is the probability of success. So in our example, I have a binomial distribution, 37 trials, probability of success is 0.54. All right, so that's the distribution we're dealing with. Exactly 19 are homeowners. So we're being asked, what is the probability that X equals 19? So on your calculator, there is, I gotta turn my light on. Can't see my note. It's getting dark outside. It must be about to rain. So probability that 19 are homeowners. That's probability X equals 19. Now, if we go to our calculator, okay, so here's my calculator. I have a binomial distribution. The DISTR button, I don't know if you can see my arrow circling, but right there, DISTR. That's my distributions. This is going to be your favorite button over these next couple of weeks. So I want to find the binomial distribution. So I go second, DISTR. And I'm going to go down to, and there's a good chance we're going to use all of these, everybody. I want to go down to the binomial PDF or binomial CDF. The binomial PDF you're going to use for probability of X equals something. So you're going to use the binomial PDF. That must mean a particular discrete function value. And then if you had to do like probability of X being less than or equal to 19, you'd use binomial CDF. Okay, that means cumulative. All righty. So in our problem, we want to use the binomial PDF, right? Because I want a particular value. So I go up one to that one. Then it's going to ask you some questions. How many trials do we have? Well, we got 37 trials. Our probability is 0.54 of success. So I put 0.54 there. We want to find out what's the probability that you have exactly 19 successes out of 37 in the trial. So you put 19 there, paste it, and lo and behold, it brings it out to the work screen, hit enter. So that's the probability that exactly 19 Americans own out of the 37 randomly selected, probability that exactly 19 of them own a home is 0.1237. All righty. Now, probability that at most 20 of them are homeowners. So a lot of students have trouble with these at most and at least. So probability of at most 20. So that's probability that 20 own homes plus probability that 19 own homes plus probability that 18 own homes, all the way down to probability that no one owns a home. All right. So probability at most 20 is going to be probability. Oh, I got to put my drawing on here. So this is probability that X is less than or equal to 20. So for that one, we're going to use binom CDF. And what the binom CDF does is it gives you the sum, like you're going to have little vertical bars that represent the probabilities, right? So CDF is going to add up all those probabilities less than or equal to 20. All right, so it's going to add up all those probabilities. All righty, so when we do at least 19, that's going to be a different calculation we're going to have to make. But greater than or equal to 20, we're going to do binom CDF, 37 trials, 54% success rate, comma 20, and that's going to give us the probability that at most 20 of them are homeowners. So let's go to the calculator. We go second distribution again. Use my arrow. This computer one's really slow. So binom CDF, we got 37 trials. 0.54 is my probability of success. My X value is 20. So because we're using the CDF, it's going to add up all the probabilities from 20 all the way down to 0. Hit enter, paste, enter again. So 56.62% of those people surveyed are going to own a home. Or that's not what it's saying. At most 20 of them are going to be homeowners. So none, the probability that none were a homeowner plus probability of one were a homeowner, all the way up to probability that 20 of them are homeowners, are going to add up to 0.5662. All righty. Now we get into the tricky little devil. This next one's a tricky. So at least 19 of them are homeowners. So what we're being asked to do is we're being asked to do probability that X is greater than or equal to 19. Well, that's going to be 1 minus the probability that X is less than or equal to 18, right? Because this is the probability that 0 plus 1 plus 2 plus 3 all the way up to 18. And then, so you subtract that from 1, and you're going to get the probability of 19 and above. All righty. So this is the calculation we're going to have to make this time. We're going to have to do 1 minus binom CDF, and we do 37, 0.54, 18. Wendy does a really good job explaining this in her video. All right, so I'm going to leave it to her to teach you the topic, and leave it to me to demo it on homework more so. Okay, so here we go. I go out to the calculator. We're going to go 1 minus this time second distributions down to binom CDF. And then enter, and then trials 37.54, stay in there. Now we go to 18, paste, enter, and hopefully 0.6882 is the correct answer. See, 0.6882. All right. Now, last one on this one, probability that between 18 and 24. Right, so if you think about it, you want a sum of the bars that have 18, 19, 20, 21, 22, 23, and 24. Basically, we want to add up all those, right? 18, 19, 20, 21. So this is 18 up to 24. So what we would have to do kind of is we'd find the probability of X being less than or equal to 24. So that's going to go all the way down to 0. And then we would subtract off the probability that X is less than or equal to 17. Reason being is we want to include 18. So then we'd have to subtract off all these ones down here. So take the whole probability from 0 to 24, subtract off the probability from 0 to 18, and you got your winning probability. All right, so to do that on our calculator, we would go distribution. I wonder if I go up instead. Hey, if I go hit the up arrow, I get there quicker. So binom CDF, luckily it saves the trials and the p-value. Now I want to go to 24 right there. And then I subtract off second distribution using the up arrow and around the horn, binom CDF. This time, the same trials, same p-value, X value of 17 this time. Paste that bad boy. And we got 0.7269. So 72.69% of the time, between 17 and 24 people would answer that they're homeowners. 0.7269. Alrighty, so that's the way the binomial theorem works. The binomial distribution. Binomial theorem, something totally different. If you're in Math 111, you probably saw that one. All right, so that's binomial. So before I scroll, what questions? No questions?
For that, for D, how did we get to that number? Sorry, I spaced on that part.
0.7269.
Yeah,
Well, I use the calculator to do that. Right, the binomial, if you see, can you see my calculator over here still?
yeah,
Yeah, so you just use the binomial CDF 2 times. So you do the binomial CDF 37, 0.54, 24 minus the same thing with 17 instead of 24.
okay.
Does that make sense, Ponce? Kind of.
Yeah.
And between 18 and 24, I do the binomial CDF function on the calculator does less than or equal to. So I went less than or equal to 24, and I have to subtract off less than or equal to 17. So if you did less than or equal, if you did the 24 and the 18, it wouldn't count the 18s, but it would want you to subtract them out. Or am I saying that right? Yeah, if you put the 18 in there, it would subtract out the probability that x equals 18. That's why we used 17. What else before I scroll down? I know it's an awful lot today. All right, so this one works the same way. So you would do the same kind of deal. Same thing with 11 and 12. All right, so 13 now uses a different approximation, uses this or this different distribution, this Poisson distribution. So read up on that in the book, watch Wendy's video. So if P is 2% and N is 400, is the Poisson distribution a reasonable approximation of the binomial distribution? So if you have a low probability and a high number of trials, then yes, you can use Poisson to approximate binomial. All right, what is the mean of this binomial distribution? So the mean of a binomial distribution, we didn't go over that in the last one, but a mean of a binomial distribution is going to be equal to the number of trials times the probability. So in this case, we're going to do 400 times 0.02. So I believe that equals 8. So that is going to be the mean of that binomial distribution. What's the actual standard deviation of this binomial distribution? So for binomial, you have the mean is defined to be that formula right there, mu equals NP, and the standard deviation is the formula square root of NPQ. Q is the probability of failure. basically you either succeed or you fail, right? I wouldn't look at it as succeed. Did they use the word succeed and fail? But fail doesn't necessarily mean you're failing, right? Like in the case of the homeowners, probability of success would be the people who have a home 0.54, probability of failure, not really a failure, right, is 0.46, because they would have to add up to 1. So in this case, I would have square root of 400 times p is 0.02. So probability of failure in this case is 0.98, because these two got to add up to 1. The p and the q add up to 1. So then I go to my calculator, and I'm going to go second square root of 400 times 0.02 times 0.98. And I get 2.8. That would be my standard deviation in this case, 2.8. All right. What is the standard deviation of the approximate Poisson distribution? Okay, so the Poisson distribution, here's the formulas for that. Poisson distribution, the standard deviation, where do I have it? It's just going to be square root of mu. And mu is the same thing, I believe. It's going to be that n times p. So mu is going to be n times p, so 8. So it's going to be square root of 8 in this case. Square root of 8 is 2 point, what do I got? Does it give me a decimal? So square root of 8. 2.8284. 2.8284. What do you think? Are those two pretty close? They are pretty close. So are these values in reasonable agreement? Yes, they are. Okay. But that's nice and everything. But let's get into the ones where you actually have to do some calculating with the calculator, with the DISTR button. But what questions of that one? All right. Moving on. We got like 14 minutes. Assume a random variable x follows a Poisson distribution with a mean of 5. So they use the big P to find to indicate Poisson. They be very careful because it stands for probability in some cases, but when you see x and squiggly here, x is a Poisson distribution with mean mu. That's what it's saying. So for probability of x equaling 3, we're going to use I think they spell out the whole word, Poisson PDF. So the particular value, and I believe they just asked for the mean and the x value. Let's see, let's go to the calculator and find out. So we go to the calculator, we go second distribution, go up to Poisson PDF. Yeah, they spell out the whole word. And then they use lambda. That's the Greek letter lambda. You're learning all sorts of Greek tonight. They use the word they use the letter lambda for mean. Gosh, I can't even talk. Use the word lambda for mean. So lambda is the mean. So we would do Poisson PDF. You're going to put that mean in, which is 5. And then they're going to want the x value, which is 3. And then you'd paste it to the outside bar there. Okay, so 5 is going to be the lambda. and then my X value is 3. And then I want to bring it out to the work screen, paste it, boom, so I get 0.1404. So 14.1% of the time, there's going to be 3 occurrences within a certain time frame or whatever, if the mean is 5.1404. And make a lot more sense what Poisson means if we do the next one, it'll make more sense. The random variable X represents the number of computer hardware help requests received at a help desk in 1 hour, and it has a Poisson distribution with a mean of 0.82. Okay, so the mean is actually equal to the variance in a Poisson. The mean equals the variance if we use that lambda instead. And then so that means that the standard deviation is basically going to be the square root of that mean, right? If I square root both sides. So the mean is 8.2. Then I would square root 8.2. Whoopsie. Second square root 8.2. So 2.8636. 2.8636. And lo and behold, we just using the formulas for those. So those aren't that bad. So the variance is always the same as the mean for a Poisson. And then you just square root that to find the standard deviation. Right, what questions before we see? Let's take a look at what we're up against in the last part of this assignment, but what questions before that? Okay. So what do we have? 16, 17, 18, and 19. 19 goes back to the beginning. You just do the expected value. You can use the spreadsheet to do that. But let's look at 16. Dandelions are studied for their effects on crop production and lawn growth. In one region, the mean number of dandelions per square meter was found to be 10.3. Okay, so I have a mean of 10.3. So we want to find the probability that you got 0 dandelions in an area of 1 square meter. Okay, we want to figure that out. The mean's 10.3, and we want an X value of 0. The 1 square meter doesn't really come into play in the calculation. So we would just go to our calculator, hit second distribution up to Poisson. We want a particular value again. So PDF, the mean was what? 10.3. 10.3. And we want to find the probability that 0 happens. So paste that, and we get basically 0. Basically 0 probability. 4 decimal places. This is times 10 to the negative 5. So if we did 0.00003, oh, I got it wrong. They put 0. So they rounded to the nearest 4 decimal places and basically got 0. So, hey, I don't see any dandelions in my yard right now. My probability wouldn't have been 0. So probability of at least 1 dandelion. Well, here's the deal. If probability of having 0 dandelions is 0, then there's got to be at least 1 dandelion, right? So you're probably going to have 100% or 1 for that probability. So then the probability of having at most 2 dandelions. So at most is going to be the CDF one then. So we would use the Poisson CDF for cumulative. So let's see what the Poisson CDF asks for when we do it on the calculator. So second distribution, Poisson CDF, we had a 10.3 mean. We want to go up. It does the same thing as the binomial. So for the CDF is going to do less than or equal to whatever you put in for the X value. So I'm going to put 2 in for my X value. I'm going to paste it 0.0022. So 0.22% of the time, you're going to have less than or equal to 2 dandelions. There's gonna be a lot of dandelions in that square meter, apparently. Somewhere along the line. Let's do another one of those. Let's do the next one. Radioactive atoms are unstable because they have too much energy. When they release their extra energy, they are said to decay. When studying a particular radioactive element, it is found that during the course of decay over 365 days, so that's your time frame, 1 million radioactive atoms are reduced to 988,607 radioactive atoms. Find the mean number of radioactive atoms lost through decay in a day. All right, so a mean number in a day, we would actually do 1 million. One more zero, minus 988,607. That's the decay over 365 days. So to figure out how many happen in one day, I would divide that by 365. Remember, on your calculator, when you do divisions, you always got to encapsulate the entire numerator and entire denominator, or you could end up in trouble. So let's see, 1 million minus 98860, whoops, 07 divided by 365. So mean number of atoms lost a day is 31. Where do we want to go to? Does it give us a rounding? So if I just said 31.2, is it going to give it to me? It did. It let me round it to the nearest 10th, which makes sense according to week 1, since, you know, 1 million and this other number rounded to the nearest whole number. So if we're going to round something based on those calculations, we should round to 1 extra decimal place, or the 10th. So now, probability equal to a value, you're going to use the Poisson PDF. So second distribution, go up to Poisson PDF. Oh, I went too far. Quit. So Poisson PDF. The mean was 31.2. We want to find out what's the probability that 26 decayed on a given day. So then we get 0.0493. 0.0493. Incorrect. What does it want? 0491, huh? Did I put something in incorrectly? All right, anyway, that could be one of those cases where if you come across that on your homework, just let me know and we can go back and override it. Because isn't it 26, 31.2, x equals 26. Oh, I use CDF. Man, struggle's real. .0493. and they got 0.0491. They must have extended out the decimal places for the mean. They must have extended this when they did this calculation. So like I said, if you come across that in the homework, just let me know and we'll go, I'll look at it, and chances are it's just a rounding scenario and I can override it and give you full credit. All right. So the last one looks like this. And basically for a recent period of 100 years, there were 76 major earthquakes. Assuming that the Poisson distribution is a suitable model, find the mean number of earthquakes per year. 76 major earthquakes in 100 years. The mean is going to be 76 divided by 100, or 0.76. And then you're going to use that Poisson PDF for the first 5 for, let's do 6 or more. And then I'm going to call it a night because it's 6:20 now, or 6:19. So probability of 6 or more. That's probability X is greater than or equal to 6. Probability X greater than or equal to 6 is 1 minus the probability that X is less than or equal to 5, right? So I would do this on my calculator then. We're going to do 1 minus Poisson CDF cumulative, and we use 0.76 as the mean and 5 as my X value, and hopefully this works out correctly. Let's see, 1 minus second distribution Poisson CDF 0.765 paste. Oh, 0.0001 then. Let's see. 0.0001. Good. It gave it to us. This E-4 is a scientific notation deal. All right, everybody. Okay, any last minute questions? Because it's time. This is 4:30 to 6:20, right? I had the day wrong when I put it on the syllabus, so I'm pretty sure it's 4:30 to 6:20. Yeah, so message me right from My Open Math if you have questions, or come to office hours Thursday 10 to 10:30 or 4 to 5. Okay.
I have a quick question. When we have like an exam, are we able to use notes?
Yeah.
Okay, because I've been taking notes for all the formulas, but I was like, my brain is like really full now.
It'll be a rough go. Yeah.
Okay.
Definitely use notes, and I'm probably gonna put I'm undecided about a practice test yet, because all of the exam questions come from the homeworks.
Okay.
So, I mean, if you know how to do all the homeworks, the exam will be pretty, there won't be any tricks. You'll have seen questions just like them before.
Awesome. Thank you.
Any other questions before we call it a day?
Quick question on exams. Are they timed?
Yeah.
Okay, cool.
But they're gonna be way more time than you need, I hope, Estelle. I mean, I got it timed out at 3 hours
Okay,
for 25 questions.
perfect.
So I'm crossing my fingers that's enough. I'll take it myself first, and whatever it takes me, then I'll figure out if I should add more minutes. I usually multiply how long it takes me by about 10. What other questions? Any?
When will the exam be, or will it be during like midterms?
Yeah, it's week 6, I believe. Week 6, so it'll open up that Sunday and close the following Sunday. So you just pick yourself a 3-hour window that you want to do it during sometime that week. All right, anything else for the good of the order, everybody?
I'm good. You have a good night. Thank you so much. That was really helpful.
Oh, good, thanks. You guys have a great night too.
Thank you.
See you later.